Hello everyone. In this video we're gonna jump all the way to chapter 14. We will go back to American options later and get into more details about it. For now we're gonna go to chapter 14. But before we do that, we're gonna do a quick review of the normal distribution. The normal distribution is gonna be used a lot. It's actually gonna be fundamental for what we're going to do the rest of the class. From now on, we're gonna try to go from the discrete case that we've been using so far to the continuous case. Now, just to refresh your memory, remember the z is the standard normal variable where the density function was this from minus infinity to infinity of 1 over 2 pi e to the minus x squared over 2. The x that this was equals to 1. Now, if x is normal 0 sigma square, which means this is the variance, then the density function looks like this. It will be the integral from minus infinity to infinity 1 over 2 pi sigma e to the minus x squared over 2 sigma squared, and this is also equals to 1. Now, in general, let's say that you want to find a new normal distribution. This is the trick we're going to use a couple times in the rest of the class. Let's say that y is a new random variable that is defined as a constant c times a standard normal distribution, which was this one, plus another constant d. Then the expected value of y will be c times the expected value of z plus d. So in this case, it will be z times 0 plus d, which is just equals to d. And the variance of y, remember by definition of variance, this will be c squared, the variance of z, plus the variance of d. Sometimes you want to make sure it's understood. Instead of writing just v, you should write variance. So then this will be c squared times 1 plus 0, which is just equals to c squared. This is not new. This is something that you should all have seen at some point in your previous math classes, especially in Math 380. Now, the part that we care right now will be the following. Let's say that you have the following variable, x, and the x is normal 0 sigma square. Okay? And let's say that you are interested in finding the expected value, and this expected value is going to be very, very, very important later. You want to find the expected value of e to the ax, where x is the random variable and a is just a constant. Okay. So by definition, expected value, this will be the integral from minus infinity to infinity of 1 over 2 pi sigma e to the minus x squared over 2 sigma squared times the function you're trying to find, which will be e to the ax. All of this x. Now here we need to use a previous result, otherwise this integral will be pretty tricky. And remember, if we have something that looks like this, you get 1. Or something that looks like this, you also get 1. Okay? So that's going to be the key to solving the problem. So we need to combine these two and complete the square. Remember that when you multiply exponents, you just add the coefficients. So for example, here we focus on this part only and just focus on the exponent. This is what we have. You have minus x squared over 2 sigma squared plus a to the x. So what we need to do now is complete the square so we can have a perfect square. So to do that, what we do is you factor this 1 over 2 sigma squared. So this will give you x squared minus 2 sigma squared ax. Remember that to complete the square, which is a topic from basic algebra, you divide whatever this is by 2 and then square. So if we do that, you divide this one by 2, then you will end up with just sigma squared a. So if you square that, you'll have sigma to the 4a squared. So you add this here, sigma to the 4a squared. However, this was not in here, so therefore you had to subtract it, but you need to subtract not only this, but this times that. If you multiply this times that, you will end up with negative sigma squared a squared over 2, so therefore that means you need to add sigma squared a squared over 2. You should check this part. Hence, you simplify this, you will end up with minus 1 over 2 sigma squared x minus sigma squared a squared plus sigma squared a squared over 2. Again, this is just completing the square, and you should definitely check that when you go through all of these steps, you end up with exactly this. So therefore, you can rewrite this as the integral from minus infinity to infinity of 1 over 2 pi sigma e to the minus 1 over 2 sigma square x minus sigma square a square dx. Notice that this part, this part is also part of the problem, but this is a constant which doesn't depend on x, so technically you can put that outside and you could write it right here. So this will be e to the sigma square a squared over 2. Remember that all of this is equals to 1. That's the only reason why we complete the square. So therefore this will give us e to the sigma square a squared over 2 times 1, which is just e to the sigma square a squared over 2. So the expected value of this, which like I mentioned a few times already is going to be very important, is just equals to this. Okay, so maybe we should make this one a little bigger. So from here, this should equals to e to the sigma square a square over 2. Okay. Then finally, related to this topic, well, let's say you have a new random variable, Kc, and let's say that Kc is equals to the constant a times the random variable x plus some another constant am. So then the expected value of e to the Kc will be the same thing as the expected value of e to the ax times e to the am. Now, since this is a constant, you can take this out. Since this is a constant, so therefore this will be e to the am times the expected value of e to the ax. But we just found out what was the value of e to the ax. E to the ax, the expected value was e to the sigma square a square over 2. So therefore, if you combine these two, you end up with e to the am plus sigma square a square over 2. Again, this result is going to be very, very useful in the coming chapters. All right, now let's jump to chapter 14. So this is chapter 14. And from here on, we'll try to make the jump from discrete to continuous. We're not gonna get to the continuous part until chapter 16, but this is the framework before we get there. Okay. The main idea in chapter 14 is that we technically will try to make things more realistic now. Remember, we've been using the binary model, which we still will be using. And the main problem with the discrete model is that in real life, the stock prices change continuously. So that's why we need to come up with a more realistic example, and the normal distribution is going to be very important for that. So the main topic on chapter 14 is the following. There's something called the efficient market hypothesis. And all that means is that the current asset price reflects all past information, which means the price for right now depends on the past only. And knowing the past can only help you to get information today, but it cannot help you to get the information tomorrow. In other words, you cannot predict the future, which we talk about that many times. Right, so the main concept here is going to be something called the daily returns. And the daily returns, by definition, is going to be defined as SOTI plus 1 minus SOTI divided by SOTI. Technically, this represents two consecutive trading days. Like, this is the stack of the price today, this is the stack of the price tomorrow. So this will represent the daily return. Right? So the first thing that you may want to consider from here is, well, what will be the average of this? Well, the average will be 1 over m, the sum from I equals to 1 to m of r of ti. Okay? And what about the variance? Well, the variance will be 1 over n minus 1, the sum of I equals to 1 to m. Notice that all of these are still just discrete variables. Okay, so this is the definition of the mean, and this is the definition of the variance. Therefore, if we want to find normalized daily returns, so this will be normalized. Remember, normalized means that the mean is 0 and the standard deviation is 1. So this will be equals to r of ti minus mu of m, tilde of m, divided by the standard deviation. Okay. All right, so the main idea right now, it will be that the daily returns are going to follow a very specific pattern, and there will be a few assumptions that we need to make. And remember, the end goal of chapter 14 and then chapter 16 is going to be to try to get to a continuous model. So here are the assumptions that we need to follow. So the first thing is you're gonna have something that is called the log returns. Remember that this means ln of s of ti plus 1 minus ln of s of ti. So by definition, log returns is defined like this. Okay. Now, if we want to go to a continuous time, that means the time interval is going to be very, very small. Okay. So if the time interval is small, then we can write this as ln of 1 plus s of ti plus 1 minus s of ti divided by s of ti. Okay. The only reason why we did this is that if the increments or the time step is very small, this is approximately equals to s of ti plus 1 minus s of ti divided by s of ti, which, remember that this is the definition of the daily returns. Again, this assumes that they are small, which means the price today, the difference of the price today and tomorrow is small. Okay. All right, so the first assumption we're going to make is that we will assume the log return is approximately equals to the daily returns. So this connection is going to be very important, that this is approximately equals to this. Okay. The next assumption is that the average of this, the average of the log returns over the period delta t. So the goal is eventually to let delta t to go to 0, and then we will have a continuous case. Okay. All right, so the assumption is the expected value of the log returns over a specific time period, delta t. Remember, so if you start in t and you move to the next step, let's say from ti to ti plus 1, this distance will be delta t. Then ln of s of t plus delta t divided by s of t, that this is equals to mu times delta t, where mu is a constant, usually is positive, and mu is called the drift of the stack. So here E is the actual probability, not the martingale probability. Okay. Notice, this is important to see. So note that when we have the bank account by definition was equals to this, right? So therefore this means that BT divided by B0 is equals to e to the RT, which implies that RT is equals to ln of BT over B0. So therefore, mu technically will play the same role as R does in this particular case, okay, for the money. The next assumption is that the variance of the log returns, again over the same time period, should equals to this, so that the variance of ln of s of t plus delta t divided by s of t, that the variance is equal to sigma square delta t, where sigma is positive and sigma is the volatility. Okay. So therefore, from this we can conclude that the log returns over a small time period of delta has, and so this is the assumption, okay, that has a normal distribution where the mean is mu delta t and the variance is sigma square delta t, which means that the log returns, okay, over the time increment, and by the time increment, it means delta t, are normally distributed. Okay. In other words, from here we can rewrite this as this: ln of s of t plus delta t is equals to ln of s of t plus mu delta t plus sigma delta t theta, where theta is a normal distribution or a standard normal distribution. Also notice that if this is the case, then this implies that s of t plus delta t can be written as this: s of t e to the mu delta t plus sigma the square root of delta t times theta. Also notice that if s of t is positive, then this is always positive. So that means the price would be always positive, which is an assumption we have been doing since we looked to forwards in the beginning of chapter 3. Right? So therefore, if this is what we get, this implies that s of t plus delta t is called a log normally distributed. And this is going to be, sometimes it's called a geometric Brownian motion, and we'll get into a lot of details on that later. Okay, let's go all the way to chapter 16 right now. So we're going to look to the limit of the discrete price model that we've been using so far, and the price of a European option in continuous time. Okay. So remember from last time, and in this case means the last page, we have the following assumptions. Okay. The log returns. Okay, this may not be the best notation, but this is what we have. This was normally distributed with mean mu s and variance sigma square s, where s is a positive value, and the expected value of the log returns, okay, that is equals to mu t, and the variance of the log returns This is equals to sigma squared t. All right, so notice the slight change here. So if we start in 0, then this will be just s of t. So here we kind of interchange the variables, but this is the exact same assumptions that we have last time. Also from way back in the class, remember we have the binomial model, okay, where s of n was equals to s of n minus 1 times 1 plus c n. Remember, this was the discrete case where c n was equals to either a or b, where the probability of this was p and this one was 1 minus p, and the value for n was 1 all the way to capital N. Okay, so remember this was the discrete model that we've been using all along. Here this is actually a n and b n. Remember that they could be different at every step. Well, let's do one exercise. Okay, and let's say that if we assume that a n is equals to a for all the values of n, and bn is equals to b for all the values of b, which means the values of a and b will not change during the tree, which we have done that before, then we want to show that the following is true. The expected value with respect to p of ln of s of n divided by s of 0, that this is equals to p ln of 1 plus b divided by 1 plus a plus ln of 1 plus a, everything multiplied by n. So this is what we want to show. Also, we're going to denote this by definition to be mu's of n tilde. Okay, so how do we show that this is true? Okay, here it is. Remember, the goal of doing these exercises is that eventually we want to show that this will give us this precisely. Okay, all right, so now let's define a new variable. Let's say that let zn to be ln of Sn over Sn minus 1. So that will be the definition, okay? Which this is equals to ln of 1 plus Cn for n equals to 1, 2, all the way to n. Well, how do we know that this is equals to this? Well, look to this part. If you divide both sides by s of n minus 1, you divide this by this, you'll end that s of n over s of n minus 1 is just equals to 1 plus Cn. So therefore you take the ln in both sides, you end up with exactly this. Right? So remember here that the random variable is Cn. So therefore from here we will get the expected value with respect to p of Zn will equals to the expected value of ln of 1 plus Cn. Okay? Now by definition of expected value, this will equals to p times ln of 1 plus b plus 1 minus p times ln of 1 plus a. Why? Because remember from here, Cn is equals to Vn, and there is a probability of p of that and a, and the probability is 1 minus p. which if we simplify, this is the same thing as P times ln of 1 plus B plus ln of 1 plus A minus P ln of 1 plus A. We can factor the P from both of this, and then you will end up with P times ln of 1 plus B minus ln of 1 plus A plus ln of 1 plus A. You use the properties of logs. Remember, this is equals to P of ln, P times ln of 1 plus B divided by 1 plus A plus ln of 1 plus A. Now, this is not exactly equals to this because the n is missing, but we're almost there. All right, next, notice the following. So notice this. The ln of s of n over s0 is exactly the same thing as this. Ln of s1 over s0 times s2 over s1, because this will cancel, and so forth, through all the way until you get s of n minus 1 over s of n minus 2 times s of n over s of n minus 1. Okay, so it's pretty easy to see this is the case because this will cancel, and you will end up only with this over this left. Now, by the properties of logs, this is the same thing as ln of s1 over s0 plus ln of s2 over s1, and so forth, until you get to the last two, ln of sn minus 1, s of n minus 2, plus ln of s of n over s of n minus 1. Remember that the ln of a times b is the same thing as ln of a plus ln of b. Okay. Therefore, you can rewrite this as the sum from I equals to 1 to n of ln of si over si minus 1, which this is actually equals to ln from I equals to 1 to n of z of I. The next thing we had to do is take the expected value on both sides. So we'll do that on the next page. Okay, so the expected value of the log returns of Sn over S0 is equals to the expected value of the sum from I equals to 1 to n of zeta I. So therefore, this is equals to the sum. You can interchange the sum with the expected value. You can do this because this is finite. Otherwise, you cannot just interchange expected values with the sigma notation. So this is what we have. But remember that this is the same thing as the sum from I equals to 1 to n. In the previous page, we calculated this part already, and the expected value of that was equals to P ln of 1 plus B over 1 plus A plus ln of 1 plus A. Now, at this point, this is a constant, and remember, when you sum from I equals to 1 to n of a constant, you just end up with C, the constant times n, because this pretty much means c plus c plus c and times. Okay, so therefore if we apply that principle, we end up with n times this one, which is the result that we wanted to get, which is equals to mu of n. Now, in a similar way, you can show that the variance, okay, with respect to p of ln of Sn over S0 is equals to p 1 minus p ln of 1 plus, sorry, this is 1 plus b over 1 plus a within a square times n. So the process is very similar to the previous one, and is equally annoying. So you should show this. I believe this is even one of the homework questions. So you want to show this. So make sure you spend the time to show that this, the variance of this, is equals to this. Just remember that by definition, the variance of x is equals to the expected value of x squared minus the expected value of x squared. So that's the definition you had to show. That's the definition you need to use. Okay, to make sure that you know how to get this part. All right, so finally, recall that t is a fixed time, and that t is technically equals to delta t times n. You have n steps. So choose A and B, where remember A is the probability of going up and B are going down, and P, so the expected value of ln of st over s0. So now we're in the continuous case, that is equals to mu t, and also that the variance of the same quantity, that this is equals to sigma square t. Okay. All right. So this is what we're gonna do. Let's say that we choose, and you'll see why we do these selections later. A to be equals to e to the mu delta t minus sigma the square root of delta t minus 1, and b is equals to e to the mu delta t plus sigma the square root of delta t minus 1. Okay. If we make these selections and we choose also p to be equals to 1/2, then this is what we have. Remember, just a few minutes ago, we showed the mu n was equals to p ln of 1 plus b over 1 plus a plus ln of 1 plus a times n. We just did this in the last page. So if we plug in these values, this is what we get. This is equals to 1/2 times ln of e to the mu delta t plus sigma the square root of delta t divided by e to the mu delta t minus sigma square root of delta t. The ones cancel each other out. That's why we pick the 1 here. Plus ln of e to the mu delta t minus sigma the square root of delta t. Okay, so pretty much all we did was plug in these values in the formula we got last time. Then if we simplify this, you just have to be very careful with the algebra. This is the same thing as 1/2 ln of e to the mu delta t plus sigma the square root of delta t plus 1/2 ln of e to the mu delta t minus sigma the square root of delta t. How do we get this part? Remember if you have a log of a division, it's the same thing as subtracting the logs. So technically this will give you minus 1/2 this, but then you have 1 in here. So minus 1/2 plus 1 gives you 1/2. So this is how we get this value here. Also remember that all of this is being multiplied by n outside, so let's not forget that we have n in here. Okay, so that's multiplying everything. So here we need to have a parenthesis. Okay. Now notice that now you only have ln in here and e. So remember that ln of e to the t is equals to just t, because the ln cancels with the e. So therefore we end up with 1/2 times e to the mu delta t, just 1/2 times mu delta t plus sigma square root delta t plus 1/2. These also cancel each other out, so you end up with mu delta t minus sigma the square root of delta t, and everything is multiplied by n. So here you can see that these will cancel, and you'll end up with 1/2 mu delta t, 1/2 mu delta t, which will give you mu delta t times the n that we have outside. But remember, by definition, t was equals to delta t times n, so therefore this is mu t, and that's it. Similarly, you can show the variance, which is equals to this by definition p1 minus p ln of 1 plus b over 1 plus a, the whole thing squared times n. That this is equals to 1/2 times 1/2 if we plug in the same values that we use here. Okay. Once you plug in the values in here, you can check that this is equals to 4 sigma squared delta t. Okay, you should verify this by yourselves, that this gives you exactly this times n. So therefore this gives you sigma square, because this one cancels that one, sigma square delta t times n, which is just sigma square times t. And that's it.